Hello, hybridization. Last video we discussed sp2, sp3 hybridization. So this video I'm going to explain sp3d and sp3d2 hybridization and also hybridization in double bond and triple bonds containing molecules. So let's talk about sp3d hybridization first. sp3 dehybridization, you can see clearly sp3 hybridization is made by mixing s orbital and 3 p orbitals and d orbitals. There are 5 orbitals mixing to make sp3d hybridized orbitals. So sp3 hybridized orbitals are trigonal bipyramidal shape. Trigonal bipyramidal shape. For example is PCl5 is one example. So how we can draw PCl5? There are 3 PCl bonds are on the plane and 2 Cl bonds are in axial positions. So PCl5, these chlorines, so 1, 2, 3, the chlorines are on the plane, we call equatorial positions, and these 2 chlorines up and down we call axial positions, axial and the equatorial. So this is how PCl5 structure looks like. So there are 5 ones, then we need to make 5 hybridized orbitals. Now let's see how we can form hybridized orbitals. So as the procedure I explained last time, first we need to pick the central atom valence shell. So central atom here is phosphorus. So phosphorus is atomic number is 15, Z is equal 15. So if you write the configuration, it is 1s2, 2s2, 2p6, 3s2, 3p3. So valence shell here is 3s2, 3p3. But we all know shell number 3 and beyond, in addition to the s and p, there are d orbitals also available, but in phosphorus it is empty. 0 electrons in d orbital, but still d orbitals are available in n is equal 3 shell and beyond. Right? Let's keep in mind and then let's move on to the orbital diagrams. If we draw orbital diagrams for 3s2, there are 2 electrons in 3s level and p level, 1 singly occupied electron in each p orbitals, in each 3 p orbitals, and there are d orbitals are available again in 3d. There are 5, looks like this, but no electrons in 3d. So this is the valence shell in phosphorus. 3s and 3p electrons are occupied, but 3d it's empty but still available in n is equal 3. Now how we can promote the electron? Let's promote the electron. One of the s electron we can promote to the d, empty d level. That way we can take 5 singly occupied electrons. So let's do the promotion step. So after promotion, 3s electron become 1 single electron and 1 electron each in 3p level. Now 1 electron in the d level. All the other d orbitals are empty. This is 3d. This is after promotion. So after promotion we can see clearly 3s, there are 3 p's and 1 d. So what happened after we mix these orbitals? 3s, 3p's and 1d. So it makes equal size and shape 5 sp3d orbitals. 1 electron in each sp3d hybridized orbitals. So these are equally shaped and size sp3d orbitals. So one lobe is large, the other side lobe is small. So this is one sp3d hybridized orbital. the same type of 5 orbitals are formed, each orbital occupied one electron. Now let's see the phosphorus, the molecule structure. On phosphorus is our central atom. There are 5 sp3d hybridized orbitals. So one hybridized orbitals, the other one, and the other one. For the axial positions, top hybridized orbital. This is hybridized orbitals 5 looks like. And last time we explained the terminal atoms, the chlorine, fluorine. So they terminal atoms, we need electron configuration in the valency shell. So in PCl5, terminal atom is chlorine. The final configuration in the valency shell is 3s2 3p5. That means we have 2 paired electrons in S and 2 paired electrons in px and py, and 1 single electron in 3p level. So this singly occupied electron in chlorine, it's a dumbbell shaped orbital overlap with these sp3d hybridized orbitals. So one chlorine's 3p orbital, and then the other chlorine's 3p orbital singly occupied, and this is another chlorine's 3p singly occupied orbital, and this is another one, and this is another chlorine singly occupied 3p orbitals. So this is how PCl5 trigonal bipyramidal molecule is formed. sp3d hybridized orbitals on phosphorus overlapped with 3p singly occupied orbital on atomic orbitals on the chlorine, each chlorine. So there are 5 terminal chlorines attached to the phosphorus atom this way. So that is sp3d hybridization. So the same way we can explain sp3d2 hybridization on octahedral geometry. Let's move on to sp3d hybridization. sp3d2, sorry, sp3d2. So you can see sp3d2 meaning is 1s orbital, 3p orbitals and 2d orbitals. SF6, sulfur hexafluoride, it is octahedral. There are 6 bonds, octahedral. So SF6 we can draw like this. Right. So SF6, 6 bonds, we need 6 hybridized orbitals to make. Sulfur is our central atom. So sulfur electron configuration in the valency shell is 3s2 3p4. So if we draw the orbital diagrams, 3s and 3p contains 1 paired electron and 2 unpaired electron like this. And in the n=3 shell, in addition to the p, there are d orbitals also available, but now all 5 d orbitals are empty, no electrons occupied at the beginning. Now let's do the promotion step. So if we promote electron from 3s to 3d, we can find only 5 singly occupied electrons, but we need 6 hybridized orbitals to make. So then we need singly occupied 6 electrons. Therefore we promote one of the 3s and one of the 3p to 3d level. Then it looks like 1 electron remaining in 3s orbital, and in the 3p all are singly occupied now, because 1 electron from 3s and 1 electron from 3p we promoted to the d level. Now there are 2 electrons in 2d orbitals like this. Right. Now we have 6 singly occupied electrons, 1 2 3 4 5 6. So these 6 1s 3p and 3d electrons we mix together to make hybridized orbitals, 6 hybridized orbitals. So we can make 6 hybridized orbitals. They are equal in size and equal in shape, one lobe is large, the other side lobe is small, they are singly occupied. So these are sp3 d2 hybridized orbitals. First we pick the central atom, and then central atom's valency shell looks like this, and after that we promote electron to get the singly occupied electrons, because we need 6 bonds, so we got 6 singly occupied electrons. And then 3s, 3p, 3d, their shapes are different to each other, so we mix the orbitals together to get equal size and shape hybridized orbitals. So after mixing we can see one side lobe is big, the other side lobe is small, equal shape, 6 sp3d2 orbitals. Now all 6 sp3d2 hybridized orbitals are located on the sulfur. So fluorine's valency shell is fluorine 2p 2s2 2p5 is the valency shell. So if we draw the orbital diagrams, 2s2 and then 2p level, there are 2 paired electrons and 1 unpaired electron. This is 2p and this is 2s. So this unpaired electron on fluorine overlap with these 6 hybridized orbitals on sulfur to make this octahedral SF6 molecule. So let's summarize what we learned so far in the previous video and this video. We discussed 5 types of hybridization techniques. First one, we discuss sp hybridization. Sp hybridization molecules are linear shape. The bond angle is 180 degrees. And sp2 hybridization is trigonal planar shape. Trigonal planar shape, the bond angle is 120. Examples we discuss here: beryllium chloride, BeCl2. Trigonal planar we discuss BF3, another example BCl3. And when we discuss sp3 hybridization, sp3 hybridization is tetrahedral. So tetrahedral bond angle is 109.5 degrees. Example methane CH4. And next we discuss now sp3 dehybridization, trigonal bipyramidal, trigonal bipyramidal. So example PCl5, PF5. And last one we discuss octahedral molecule, that is sp3d2 type. It is octahedral. So octahedral bond angle is 90 degrees. Example sulfur hexafluoride, one example SF6. So trigonal bipyramidal, there are 2 types of bond angle. Equatorial bond angles are 120 and the axial equatorial bond angle is 90 degrees. There are 2 types, and axial bond angle is, we can take 190 actually. Then there are 3 types of bond angles in trigonal bipyramidal. So these are the 5 types of hybridization, their shapes and bond angles with examples. So I'm planning to do the double bond and triple bond ethylene and acetylene molecule hybridization as my third video. So thanks for watching.